Hey everybody, here's a related rates intro continued, which we didn't quite finish in class on Friday. So the last thing I showed you was this cone visual, and we were filling it up and we were noticing how the rate of change of the height of the water was not constant throughout filling this cone up. It was quicker at the bottom and slower at the top because the radius gets larger here and that makes it longer to fill up. And in this scenario here, we have more than just two variables going on. There's not just an x and y. We have radius of the tank and the water. We have height of the water and the tank. And we have volume of the water and total volume of the tank, the capacity. And we always have this time ticking in the background. And because in related rates problems, you let things happen and change, and then you stop the timer at 1 instant, everything is going to change with respect to time. So again, when you stop the time, that's critical, because if you stop the time at 1 instant, the rates might be different than at another instant. So we're going to use derivatives, because derivatives are really just rates of change, to see how different rates of change are related to one another. Again, related. Whoa, typo. Related. So that's why it's called related rates. You want to see how rates of change are related to one another. And we're not just going to be dealing with dy dx anymore, the change in y with respect to x. We're going to be dealing with statements like this, dA dx or dr dx. And dA dx might mean something like this. The rate at which area is changing with respect to, and it's always with respect to the variable in the bottom. In this case is t, which will be time. So that's a very typical statement. You'll be writing dA dt a lot. You might also have dr dt. A statement like that could be the rate at which radius is changing with respect to time. So again, we're finding rates of change at 1 instant in time whenever we stop our stopwatch, which is ticking in the background, because again, at another time, the rates will be different. So I have a couple more visuals to show you here for related rates. You will be doing all of these. So here's the cone one. Another really typical one is the ladder problem. So let's start it at the top where it's realistic here. We have this ladder that starts at the top, and it's leaning against a wall, and it's sliding down, which you would never want to happen if you were actually using it, but let's just say it is happening. And we're saying if its bottom is pulled or pushed at a constant rate of 0.5 meters per second, how fast is the ladder sliding down when it reaches 5 meters, 3 meters, or 1 meter up the wall? So I want you to watch carefully, and we want the rate of change in here, y. Notice right there, the change in y is not constant. So let's start again at the realistic scenario. Slowly starting down. dy dt is not changing much. And boom, right there. That's when it's the quickest. And if you show the rate of change with y, you can see it's definitely not constant. It starts slow, and then as x gets larger, it quickly speeds up right there. So we will be doing a ladder problem in class. Just realize that the rate of change in x is constant, and the rate of change in y is not constant. So depending on when you stop your timer, that will determine what the rate of change in y is, because it's not the same. Another one that AP really likes is the balloon one, inflation. Here we go, inflating a balloon. So let's say we have this balloon and it's inflating at a constant rate. So you're blowing up the balloon. How fast is the radius changing when the diameter is 1 meter, 1 centimeter, 2 or 4 centimeters? So let's actually inflate this thing. Check out these amazing visuals. And notice as the balloon gets larger and larger, the rate of change of the radius is not as quick. So when you first start blowing up a balloon, the rate of change in the radius is very quick. It grows very, very obviously. And then as you start blowing more and more of the balloon up, the rate of change in radius is a lot less. So if I show the rate of change in R, at the very, very beginning, it's very quick. And then it levels off here as the balloon gets larger and larger. So those are scenarios that you will all be doing by hand, but it is helpful to see the visual just so you can kind of picture what's going on here. So rates of change are not the same, and there's several variables going on, and all the rates are related to one another. They depend on one another. So let's go back to here. And before we actually do some problems, I do want to mention that whenever we do these problems, sometimes they're going to seem very forced or cheesy or unrealistic. Like you'll have a box that's magically growing, and it's like, what kind of box magically grows? But you have to keep in mind these problems are going to be simplified so that you can actually do them by hand. A real related rates problem would be messy, would have many, many variables. You wouldn't really be able to do it at this point in your life. And it would be something like, remember the BP oil spill. So something like, how fast was the oil spill spreading? What was the rate of change in the oil spill? How much cleanup crew do we need given that rate of change? Or with the flooding that was going on down south with all the hurricanes, how fast is the rate of change of the water? How quick is the water level rising? What's the drainage capacity? Or the fires in California, what's the rate of change in the spread of the fire? All those are actual related rates problems. The ones you will be doing are going to be slightly simplified. So just keep that in mind when you do this, that some of them will be a little cheesy. Also, the AP exam does not assume you know any science formulas. You could do related rates formulas with like kinetic energy, potential energy, Bernoulli's principle, Ohm's law, but you will only be responsible for related rates problems that involve math formulas. So what I want to do is have you practice going from English to math. We're translating here 2 languages, because you won't be able to do related rates if you're not able to read something and write a math statement for it. So I'm going to do one of these with you, and then I want you to pause. You don't have to write these down. You can if you want to. You don't have to, but I want you in the corner of your notebook just to jot down what your answers would be, because they're very small. So we're going to interpret the sentences mathematically. And we're going to translate them into symbolic notation. And we're going to interpret the entire sentence, not just part of it. So in number 1 here, we have the area of a circle. It's increasing at a rate of. That immediately means derivative, because it's rates, 10 square centimeters per second. When I hear centimeters squared, I'm immediately thinking area. If it was centimeters cubed, I'd be thinking volume. If it was just centimeters, I'd be thinking distance. Centimeters squared is area per second, so there's my rate of change. And if the area is changing with respect to time, you have to think, how am I going to write the change in area with respect to time? Well, you're going to use a derivative, and it's the derivative of area with respect to time. You have to remember how we translate to math. And the rate of change of the area with respect to time is 10 centimeters second. Square centimeters per second. And because it's increasing, I'm going to keep this positive, because if a derivative is positive, the actual quantity is increasing, which is happening here. So I want you to pause and just read through these and jot down what your little statements are. You don't have to write the sentence down again. All right, so you should have by now written all these little statements down. Please check yours with mine. Anywhere it said decreasing, I made the rate of change negative, which was the case in number 2 and in number 4. Here, you could have used several variables, L for level, W for water, H for height. And you might have been thinking, what the heck is a cistern? And to be honest, I kind of thought that too when I read it. So you know what? Here's a cistern, just for your knowledge. It's a tank for holding water that's used especially for like flushing toilets, or it's an underwater tank to hold rainwater. So anyway, back to calculus. You also have this worksheet here. Make sure you had all those right, okay? You have this worksheet that should be taped in your notes. If it's not taped, can you please tape it down right now? You also got one that looked like this. That should be taped afterwards. So let's go to this guy first. You have 15 formulas. You need to know all of them for related rates. So I'm going to do a couple with you just to get you going. I want you to fill the whole thing out before you watch the next video, because if you can't do this, you can't do the video problems. So what we're going to do is take formulas. You are going to identify the formula, some geometry review here. You're going to see what derivative rules you use to do the derivative with respect to time. Remember, they're all going to be d dt. And then you're going to take the derivative with respect to time. So right here, good old pi r squared. That is for the area of a circle, obviously. And to do this, I don't really need product rule because pi is just a constant. It's not a function. And I definitely don't need quotient. I'm just going to use my basic or shortcut, whatever you want to call it. So I'm going to do the derivative of the whole thing with respect to time. That means I'm doing the derivative of a with respect to time and the derivative of pi r squared with respect to time. So derivative of a with respect to time, that would be dA dt. Derivative of A with respect to time. Pi goes along for the ride. Derivative of r squared is 2r times the derivative of r with respect to time. I need to add the dr dt because I'm doing the derivative with respect to time of this, and our variable doesn't match either of the original variables. And right here, look how cool this is. This is 2 pi r. And 2 pi r you should recognize as circumference. So the derivative of area is circumference. Let's do this guy right here, because some people had a little trouble with this one. This is good old Pythagorean theorem. It's to find side lengths for right triangles only. And this, we're just going to use our basic rule again. If I do the derivative of both sides, a squared plus b squared equals c squared. Derivative of a squared with respect to time is 2a dA dt. Plus, derivative of b squared with respect to time is 2b dB dt. The derivative of c squared with respect to time is 2c, whoa, what the heck is that? 2c dc dt. You could cancel a 2 from all of these if you want. Totally up to you. And I'm going to do one more with you here. This one. Volume equals 1/3 pi r squared h. This is for the volume of a cone. Right here, I'm going to need product rule. Check it out. I have r squared times h. These are variables. 1/3 pi is just a constant, so you can keep 1/3 pi on the outside if you want. Doesn't matter. So I'm going to need product rule and my basic rule. I'm going to show you 2 ways to do this, depending on grouping. Let's say you want to keep 1/3 pi out front. So I'm going to say derivative of volume with respect to time equals 1/3 pi. It's just going along for the ride, hanging out on the outside. So I'm going to do the derivative of the first, r squared. So 2r dr dt times the second, plus first times derivative of second. Derivative of h is 1 times derivative of h with respect to time, which is dh dt. You could also say, no, I want to make 1/3 pi my first. So I'm going to keep 1/3 pi r squared. You want to make that your f, and then you want to make this your g. You can totally do that too. In that case, you would get something like this. dv dt equals your first, I'm going to do the derivative of the first. That'd be 1/3 pi times 2r times dr dt times the second, which is h, plus first, keep it unchanged, 1/3 pi r squared times derivative of second. Either way, it's going to be the same thing if you would just distribute 1/3 pi to each of those. Totally up to you how you want to deal with it. So can you please finish filling out this whole thing here, and then tape down this thing here, and continue with the next video called Related Rates. And I'll see you in class on Monday, and I hope you have a wonderful weekend. Goodbye.